Today we're diving into the fascinating world of neural networks. If you've ever wondered how computers can recognize faces, translate languages, or even drive cars, neural networks are often behind the magic. In this beginner's guide, we'll break down what neural networks are, how they work, and why they're so powerful. Don't worry if you're new to the topic, by the end, you'll have a solid understanding of the basics. Let's start by exploring what inspired the creation of neural networks and how they mimic the human brain. Neural networks are inspired by the structure and function of the human brain. Just like our brains are made up of billions of interconnected neurons, neural networks consist of artificial neurons or nodes that work together to process information. This design allows computers to learn from data, recognize patterns, and make decisions in ways that are surprisingly similar to how we think and learn. Understanding this inspiration helps us appreciate why neural networks are so effective at complex tasks. But what exactly is a neural network? At its core, a neural network is a series of algorithms that attempts to recognize underlying relationships in a set of data through a process that mimics the way the human brain operates. It consists of layers of nodes: an input layer, one or more hidden layers, and an output layer. Each node is like a tiny decision maker, passing information along to the next layer. This structure allows neural networks to handle complex tasks, from image recognition to language translation. Neural networks are organized into layers. The first layer, called the input layer, receives the raw data. Next come the hidden layers, which process the data through a series of transformations. Finally, the output layer produces the result. Each layer plays a crucial role in how the network learns and makes predictions. The more hidden layers a network has, the more complex patterns it can recognize. This layered structure is what gives neural networks their power and flexibility. Each layer in a neural network is made up of nodes, sometimes called neurons. These nodes are the basic units that receive input, process it, and pass it on. Think of each node as a tiny calculator that takes in numbers, applies a simple rule, and sends the result forward. The connections between nodes have weights which determine how much influence one node has on another. By adjusting these weights, the network learns to make better prediction. You feed data into a neural network, it travels from the input layer through the hidden layers and finally to the output layer. At each step, nodes process the information and pass it along. This flow of data is called forward propagation. The network uses the current weights to make its best guess about the answer. If the guess is wrong, the network will adjust its weights to improve next time. This process is repeated many times during training. Weights and biases are key concepts in neural networks. Weights determine how strongly one node influences another, while biases help shift the output of a node up or down. By tweaking these values, the network can learn to make more accurate predictions. During training, the network adjusts its weights and biases to minimize errors. This fine-tuning is what allows neural networks to improve over time and handle complex tasks. Activation functions are mathematical formulas that determine whether a node should be activated or not. They add nonlinearity to the network, allowing it to learn complex patterns. Common activation functions include the sigmoid, tan, and ray-lu. Each has its own strengths and is chosen based on the specific task. Without activation functions, neural networks would be limited to solving only simple problems. See forward propagation in action. Imagine you're showing a neural network a picture of a cat. The image is converted into numbers and fed into the input layer. As the data moves through each layer, nodes process the information using weights, biases, and activation functions. By the time the data reaches the output layer, the network makes a prediction like identifying the image as a cat. This process happens in a split second, thanks to forward propagation. Neural networks learn by making mistakes and correcting them. After making a prediction, the network checks how close it was to the correct answer. If it was wrong, it uses a process called backpropagation to adjust its weights and biases. Backpropagation works by calculating the error and sending it backward through the network, updating each connection along the way. This process helps the network learn from its errors and improve over time. Training a neural network involves showing it lots of examples and letting it learn from its mistakes. The network starts with random weights and biases. As it processes each example, it uses forward propagation to make a prediction, then backpropagation to adjust its weights based on the error. This cycle repeats thousands or even millions of times until the network becomes good at its task. Training is the most time-consuming part, but it's essential for building a powerful neural network. Most neural networks are trained using supervised learning. In this approach, the network is given input data along with the correct output, known as labels. The network learns by comparing its predictions to the correct answers and adjusting itself to get closer to the truth. Supervised learning is used for tasks like image classification, speech recognition, and language translation, where we have lots of labeled data to train on. Neural networks can also learn without labeled data, using a method called unsupervised learning. Here, the network tries to find patterns or groupings in the data on its own. This approach is useful for tasks like clustering, anomaly detection, and discovering hidden structures in data. Unsupervised learning is powerful when we don't have the correct answers available, but still want the network to make sense of the information. Another exciting way neural networks learn is through reinforcement learning. In this setup, the network interacts with an environment and receives rewards or penalties based on its actions. Over time, it learns to make better decisions to maximize its rewards. Reinforcement learning is used in game playing, robotics, and self-driving cars, where the network must learn from trial and error. There are many types of neural network architectures, each designed for specific tasks. The most basic is the feed-forward neural network, where data moves in one direction from input to output. More advanced types include convolutional neural networks (CNNs) for image processing and recurrent neural networks (RNNs) for sequential data like speech or text. Each architecture has its own strengths and is chosen based on the problem at hand. Feed-forward neural networks are the simplest type. Data flows in one direction from the input layer through hidden layers to the output layer. there are no loops or cycles. This straightforward design makes them easy to understand and use for basic tasks like classification and regression, while simple, feed-forward networks form the foundation for more complex architectures. Convolutional neural networks, or CNNs, are designed to process visual information like images and videos. They use special layers called convolutional layers to detect patterns such as edges, shapes, and textures. CNNs are widely used in computer vision tasks, including facial recognition, object detection, and medical image analysis. Their ability to automatically learn features from raw images makes them incredibly powerful. Current neural networks, or RNNs, are built for handling sequential data such as text, speech, or time series. Unlike feed-forward networks, RNNs have loops that allow information to be passed from one step to the next. This makes them ideal for tasks where context and order matter, like language modeling or speech recognition. RNNs can remember previous inputs, giving them a kind of memory. And a neural network has many hidden layers. It's called a deep neural network. These networks can learn very complex patterns and are the backbone of deep learning. Deep networks are used in advanced applications like natural language processing, autonomous vehicles, and even playing complex games. The depth allows them to extract features at multiple levels, from simple edges to complex objects. Training data is the fuel that powers neural networks. The more high-quality data you have, the better your network can learn. Data needs to be labeled and representative of the real-world problem you're trying to solve. Without enough good data, even the most advanced neural network will struggle to perform well. That's why collecting and preparing data is a crucial step in any neural network project. In training neural networks, it's important to avoid overfitting and underfitting. Overfitting happens when the network learns the training data too well, including noise and details that don't generalize to new data. Underfitting occurs when the network is too simple to capture the underlying patterns. Balancing these two is essential for building models that perform well on real-world tasks. To prevent overfitting, neural networks use regularization techniques. These include methods like dropout, which randomly turns off some nodes during training, and weight decay, which penalizes large weights. Regularization helps the network focus on the most important patterns and improves its ability to generalize to new data. Choosing the right technique depends on the specific problem and dataset. Loss functions are used to measure how well a neural network is performing. They calculate the difference between the network's predictions and the actual answers. Common loss functions include mean-squared error for regression tasks and cross-entropy for classification. The network tries to minimize this loss during training, which means it's getting better at its task. Optimization algorithms help neural networks find the best weights and biases to minimize the loss function. The most popular algorithm is called gradient descent, which adjusts the weight step by step in the direction that reduces the loss. There are many variations like stochastic gradient descent and atom, each with its own advantages. Choosing the right optimizer can speed up training and improve results. Learning rate is a key parameter in training neural networks. It controls how big the steps are when updating weights. If the learning rate is too high, the network might miss the best solution. If it's too low, training can be very slow. Finding the right learning rate is a balancing act and often requires some experimentation. In training a neural network, data is often processed in small groups called batches. The batch size determines how many examples are used in each update. An epoch is one complete pass through the entire training dataset. Using the right batch size and number of epochs can make training more efficient and help the network learn better. Make sure a neural network works well. We use validation and testing. After training, the network is evaluated on new data it hasn't seen before. The validation set helps tune the model during training, while the test set checks its final performance. This process ensures the network can handle real-world data, not just the examples it was trained on. Transfer learning is a technique where a neural network trained on one task is reused for a different but related task. This saves time and resources, especially when you don't have much data for the new task. For example, a network trained to recognize animals can be adapted to identify specific breeds. Transfer learning is widely used in computer vision and natural language processing. One of the most popular uses of neural networks is image recognition. Networks can be trained to identify objects, people, animals, and even emotions in photos. This technology powers features like facial recognition on smartphones, automatic photo tagging, and medical image analysis. The ability to learn from thousands of examples makes neural networks incredibly accurate at visual tasks. Neural networks are also used in natural language processing, or NLP. They help computers understand and generate human language. Applications include language translation, chatbots, sentiment analysis, and voice assistants. By learning from large amounts of text, neural networks can grasp grammar, context, and even subtle meanings in language. Neural networks have made headlines by mastering complex games like chess, Go, and video games. By learning from millions of moves, they can develop strategies that rival or even surpass human experts. Reinforcement learning is often used here, where the network learns by playing and receiving feedback. These achievements showcase the power and flexibility of neural networks. Self-driving cars rely heavily on neural networks to understand their surroundings and make decisions. Networks process data from cameras, radar, and other sensors to detect objects, recognize traffic signs, and plan safe routes. This technology is transforming transportation and promises to make travel safer and more efficient in the future. In healthcare, neural networks are used to analyze medical images, predict diseases, and personalize treatment plans. They can spot patterns that doctors might miss and help diagnose conditions earlier. Neural networks are also used in drug discovery and genomics, speeding up research and improving patient outcomes. Despite their power, neural networks have limitations. They require large amounts of data and computing power to train. They can also be sensitive to small changes in input, leading to unexpected results. Understanding these limitations helps us use neural networks responsibly and avoid overestimating their abilities. Neural networks are often called black boxes because it's hard to understand how they make decisions. Even experts can struggle to explain why a network made a particular prediction. This lack of transparency can be a problem in critical areas like healthcare or finance, where understanding the reasoning is important. Researchers are working on ways to make neural networks more interpretable. Techniques like visualization, feature importance, and attention mechanisms help us see which parts of the data the network is focusing on. Improving interpretability builds trust and allows us to use neural networks in sensitive applications with more confidence. As neural networks become more common, ethical considerations are increasingly important. Issues like bias, fairness, and privacy must be addressed to ensure these systems are used responsibly. Developers need to be aware of potential risks and take steps to minimize harm, especially when neural networks are used in areas that affect people's lives. Neural networks are evolving rapidly. Recent advances include transformer models, which have revolutionized natural language processing, and generative adversarial networks (GANs), which can create realistic images and videos. These breakthroughs are pushing the boundaries of what neural networks can do and opening up new possibilities in AI. Powerful hardware is essential for training large neural networks. Graphics processing units, GPUs, and specialized chips like TPUs speed up training by handling many calculations at once. Advances in hardware have made it possible to train bigger and more complex networks, driving progress in AI research and applications. Many open-source tools make it easier to build and train neural networks. Popular frameworks like TensorFlow and PyTorch provide ready-made components and tutorials for beginners. These tools have democratized AI, allowing more people to experiment and innovate with neural networks. If you're interested in building your own neural networks, start with simple projects and gradually tackle more complex tasks. There are many online courses, tutorials, and communities to help you learn. Experimenting with real data and solving practical problems is the best way to deepen your understanding. Future of neural networks is bright. As technology advances, we can expect even more powerful and efficient models. Neural networks will continue to transform industries, create new opportunities, and solve problems we haven't even imagined yet. Staying curious and open to learning will help you keep up with this exciting field. Let's recap what we've learned. Neural networks are inspired by the brain and consist of layers of nodes connected by weights and biases. They learn by adjusting these connections through training. Different architectures like CNNs and RNNs are used for specific tasks. Applications range from image recognition to healthcare and beyond. While powerful, neural networks have limitations and ethical considerations to keep in mind. If you're just starting out, focus on understanding the basics before diving into advanced topics. Practice building simple networks, experiment with different datasets, and don't be afraid to make mistakes. Learning neural networks is a journey, and every step brings you closer to mastering this powerful technology. Congratulations, you've taken your first steps into the world of neural networks. With a solid understanding of the basics, you're ready to explore more advanced topics and applications. Keep learning, stay curious, and remember that neural networks are a tool. How you use them is up to you. The possibilities are endless, and your journey is just beginning.